Right now we have discussed some of these ranges, right? We have a range, we have a lower and an upper bound, and there is some uncertainty about whether where we are going to fall in between this range. Think of two spinners, one for probability for an event, and another one symbolizing the size of the loss. Keep in mind what we're doing. We're discussing Monte Carlo simulation. It was the alternative to multiplying two numbers together in a risk matrix, right? How do we actually go about doing that in another way? And here I'm introducing these spinners as an example of these many trials that we're going to be using. We heard the word 10,000 trials, right? Or the term 10,000 trials. This is what we're talking about here. Imagine that you have an event where you know that there is a 5% chance for this event to occur. Well, it would look like this. That every time the spinner lands in those 5%, I would have an event. So on each spin, I'm gonna spin it, and I'm gonna ask the spinner, did you produce an event or not? I'm gonna end up with 10,000 spins, and how many of those spins is gonna be landing on the event? Well, 5% of them, right? If it's totally random, then 5% would land in that green area. Think now of the other side of the equation, right? We know that we have for risk, we have the probability times loss, right? Well, we do a spinner. We ask it each time we spin, did you cause an event or did you not? That's okay. That's understandable. Now we're going to look at the loss side. The loss side becomes a little bit more, you could say, complex. Here we have a spinner again, but imagining now that you have a graph that is able to translate a number from 0 to 1 into a number in your range. How would that graph look? I drew one here. So let's try to spin the spinner together. First time we got 0.25, right? Where does that end up in my range? My first number that I'm going to pick is going to be in the lower end of my range. I'm going to do it 10,000 times. So now you see that I'm going to be pick a lot of numbers from down here. I'm going to write them down, and I'm going to say, okay, how much did you cost, dear event, when you occurred? And then the nice trick comes now. I have an equation here, 10,000 equations. And this is for each of the scenarios. Let's just stick with one scenario. We know what a scenario is, right? Okay, what is the equation? How does it look for the first spin? Let's see. No event times, and let's say my number that I got from my range by my translation graph that I did, that was 15,000. Well, no event times 15,000 produces 0. All right, and imagining that happening all the way down here because it had a very 5%, so it's only going to produce an event 5% of the time. But imagining down here at number 25 trial, we actually have one event, a 1 times, and this time it was 125,000. Try now in your mind just to populate this table all the way down with 3 different or 4 different scenarios. We are able to ask better questions now. We're able to ask questions like, what does my average loss look like for scenario 1, for scenario 1 and 2, for the whole portfolio of scenarios? And wait, what's the chance for me of losing more than X amount of money in a year? Well, that is basically just going back to this table and counting how many of the times where my events produced a number that was higher than whatever I want to know the answer about. And if you do this for all numbers, you can actually make what we call a loss exceedance graph. So here we have the percentage of the trials, the 10,000 trials that exceeded some amount, and the amount is down here, right? That's going to be my monetary value here. So in the beginning, when the loss is very low down here, maybe all of my scenarios, they exceeded 0. They were larger than 0. Okay. And as I go down into more and more expensive losses, I see that the probability of exceeding that loss is going to be smaller and smaller and smaller. So this was just a very quick introduction into what is Monte Carlo 101. What I would invite you to look further into is concepts like this translation that is called the inverse distribution, F inverse distribution. And there are lots of types. Right now, I just drew one that could be a normal distribution. You've heard about that, right? That's the bell curve. At log normal, that has a fatter tail. It has a skewed body and fatter tail. We have a bunch of distributions that we could throw out there to translate that 0, that spinner, into actual loss. And each of them distribute the losses differently. So for some events, I might want to have a very fat tail, meaning that I have quite a big amount of probability for extreme events. Other types of distributions have maybe symmetric, meaning that there is an equal chance of getting something small, that there is getting something big. So that's all like it's all modifiable, you could say.